Hello, everyone. Welcome to Foresight Space Group. Today, we're really lucky to have Matthew Alcock with us. He's a space weather consultant and has recently led a project to de-risk critical national infrastructure in the UK. And he's also worked with the European Space Agency. He worked at EDF Energy, which is Europe's biggest nuclear energy provider. And he was working to ensure that nuclear power stations are resilient to space weather. He's also a fellow in the Foresight 2025 cohort of Space Fellows. So today he'll be joining to present on how to build critical infrastructure resilient to space weather. So thank you so much, Matt.
Thank you very much for the intro. Yeah, so I'll try and cover how to build infrastructure that's resilient to space weather. And this is definitely not a question or a statement that we have like one clear answer to. It will depend a lot on what infrastructure is being built, whether it's in space, in the atmosphere, on ground level. But I think there's some key principles that I think we can follow, and perhaps that haven't been followed in the past, that will get us to a more resilient future, especially when we're talking about big, long distance, long time duration journeys in space and getting more and more critical infrastructure in space. As Lydia said, I'm one of the 2025's Foresight Institute Space Fellows. I've also fairly recently quit my day job to go independent as a space weather consultant. So I'm working with a few different clients as an independent now, which means that I don't have to abide by the corporate headshot rules. Hence why my cat is also making an appearance on the first slide. And so he's with me. He may even join for this call. He often comes in shouting when I'm speaking. Okay, so what are we going to cover? We'll cover what space weather is, how and in what way it's a risk to critical infrastructure as a natural hazard, space weather extremes, which are particularly important from a risk perspective, because those are the things that those are the events that can cause most damage and are perhaps the events that are least mitigated against in certain industries. Then we'll cover what space weather services are available and how these can be used to improve space weather resilience. And then I'll try and answer the question as to how we can keep critical infrastructure operating during severe space weather. So firstly, what is space weather? Hopefully my video will work. So space weather is an umbrella term for a variety of different phenomena that originate from the sun and cause interactions and effects on Earth, its atmosphere, and the near space environment. So it covers things like solar flares, coronal mass ejections, solar radio bursts, and other explosive phenomena that originate from the sun and can, if we're unlucky, disrupt infrastructure on Earth and in the near space. So this video is cycling through various different observations of space weather conditions, some of which are observed using space-based monitoring systems. So things like this, we're seeing a prominence erupt from the sun, which is the progenitor for coronal mass ejections, big balls of plasma that fly out into space due to the energy generated from the reconnecting magnetic field on the sun. And then if we're unlucky, then the Earth is in the middle of where the coronal mass ejection is going, and that can cause various disruptions that we'll get into. This video in blue shows a coronal mass ejection that's heading straight towards the camera, which is on the Sun-Earth line at the L1, the Grand 1 point, and shows some of the ways in which the plasma and radiation can disrupt. And the camera's on board showing that white snow. Let's go back to it. Yeah, showing the speckles of radiation interacting with the camera on board the spacecraft. Here we have a simulation, or results of a simulation, showing the solar system from the top down. You can visualize here how the plasma flows through space. And this is a simulation again of the near Earth space. So it's showing the Earth and its mostly dipole magnetic field, illustrated by these field lines. And then this is very much a sped up illustration of how a geomagnetic storm can progress over the course of a few days. So basically what we're seeing here is how all of the magnetic field of the Earth is being compressed and energy is being added, and we're getting reconnection of magnetic field lines causing geomagnetic storms, substorms, and various different phenomena. So all of this energetic space weather phenomena follow what's called a solar cycle. which in the case of our sun is fairly consistent at about 11 years. So this is where the sun is oscillating between periods of solar minimum, where we have not very much space weather. We have a more uniform sun, as we had in around 2010 and 2020, where there are not very many sunspots, not very many solar flares. And it oscillates up to solar maximum, where we have more solar activity, more sunspots, so where sunspots would occupy the Earth-facing portion of the sun almost every day. And it's in these periods where we get more solar flares, more coronal mass ejections, and potentially more space weather effects. We have data of this solar cycle showing this predictable 11-year cycle going back for many hundreds of years, and even further when we consider proxy data in using radioisotopes in tree rings and ice cores. And on top of the 11-year cycle, that some of the peaks and some of the troughs are higher and deeper than others. This is a much less well understood part of the solar cycle, these higher order oscillations in the sun's activity, where we have periods of maxima that don't really reach very high. The number of sunspots it remains quite low. And then other periods where we have many more sunspots. And this is still quite poorly understood. Yet NOAA and NASA and the like try and predict these kind of things to some success, but often to some failure because it's still fairly poorly understood. We're currently at around about solar maximum, which is why you've probably seen over the last year or so news articles about some fairly big geomagnetic storms, even some disruption of satellites as well. So space weather as a natural hazard. So this is one of the images that you'll often see in space weather talks from ESA, just illustrating all of the different ways that space weather can impact different infrastructure, from satellites and astronauts in space, radiation damage to electronics that can potentially cause complete loss of satellites, and down into aviation altitudes where crew and passengers can receive higher radiation doses, and avionics can be disrupted, causing disruptions to things like autopilots. And then towards ground level, the main impacts are through geomagnetically induced currents in power systems. So these long cables that are used to transport electricity to our homes and businesses, these can be damaged through, or rather the transformers that connect these wires can be damaged through these induced currents. Space weather should be thought of in the same way as we think of terrestrial weather, in that it's an umbrella term for lots of different phenomena. It's not just one risk, and rather it's a collection of different phenomena that have different predictive capabilities and different effects on different infrastructure. So in the same way that terrestrial weather can affect different infrastructure in different places in different ways, through tornadoes in one place and high air temperatures in another place, high winds in another place, we have an equivalent menagerie of effects that can be caused by space weather. And whereas one aspect of space weather can be effective to one infrastructure, it may not be effective to another infrastructure or another part of the world. This graphic is one that I created for a recent policy paper that I published that just tries to capture at a very high level some of that complexity, indicating how the sources of the solar phenomena, solar flares, coronal mass ejections, and the like, can have causal connections to the phenomena in the heliosphere, magnetosphere, and then what hazard they pose to infrastructure on Earth, in the atmosphere, and in space. There's quite a lot to dive into here, but we'll take it bit by bit, starting with risk to satellites. So satellites are vulnerable to radiation, and this can be both during solar energetic particle events and also during geomagnetic storms, which can enhance the Earth's radiation belts if the satellites are passing through those. So solar energetic particle events are transient events where mostly protons are accelerated to extremely high energies and can cause what's known as single event upsets in satellite electronics. This is a fairly well-known issue in the industry, but the most extreme fluxes are perhaps under-prepared for. The satellites that are in low Earth orbit can also experience increased drag as the thermosphere expands during during geomagnetic storms caused by coronal mass ejections. During these periods, there may be requirements for additional maneuvers of satellites to maintain their orbit. Sometimes that's not possible, and satellites have been lost, such as was the case in 2022, where around 40 of Elon Musk's Starlink satellites were lost as they were in a transitory orbit, staging orbit before they got to their final orbit. And this was due to the thermospheric drag being greater than was expected.
Can I ask a question about
Yes,
that?
please.
On the two plots in the upper right, the first plot, can you tell me what's going on there? Okay, the blue curve is the solar flux per storm proxy.
Yeah, exactly.
Black curve, what does that black curve mean?
So the black curve indicates the number of satellites that are actively maneuvering through SST, space surveillance and tracking. Some of that, there's a baseline level of number of maneuvers that are being undertaken, and it just indicates that following this fairly major geomagnetic storm, the number of maneuvers was much, much higher to accommodate the changing orbits that had occurred due to the effects on drag.
Thank you.
I have, just as a side note, I've packed quite a lot into these slides, so there might be a few plots that I'll jump over. So do feel free to stop me if there's any that particularly pique your interest, as Creon did. So, as well as the satellites themselves being at risk, the signals that the satellites are trying to convey between satellites and to Earth-based receivers can also be disrupted. So this means that space-based services can be vulnerable. So this includes things like GNSS, the global navigation systems, SATCOMs, and various other space-based services, which can occur due to what's known as ionospheric scintillation. So as certain frequencies of radio waves pass through the ionosphere, frequencies that would normally pass through can be reflected or absorbed due to the changing dynamics of the ionosphere. In this image on the right-hand side, indicating which latitudes and which regions are most vulnerable to this, and it's mostly around the equator and around the poles. And you'll see around the equator, it also illustrates the southern Atlantic anomaly, where the Earth's spin axis and magnetic axis are misaligned, giving regions that are interacted more with the Van Allen belts. So coming closer to Earth, there is also a risk to aircraft. So during those extreme solar energetic particle events, some of the highest energy particles, which requires an energy of about 1 gigaelectronvolt, can reach the atmosphere and trigger a shower of secondary particles on aircraft, and some of which can even reach ground level. Most of these secondary particles are neutrons, which can cause single event upsets to electronic components in aircraft. So there was one event in 2008, which often gets cited as a potential impact caused by these secondary particles, Qantas Flight 72, which experienced a major failure in their autopilot, and the flight took unsolicited nosedives at several points during the flight, during which anything that wasn't tied down or seatbelted in was accelerated towards the ceiling, and there were inevitable injuries that followed from this, many of which were really quite serious. And I recommend the book No Man's Land, which was written about this event by the pilot, who then suffered quite serious post-traumatic stress and was unable to work following this event due to the nature of the industries and the responsibility that he had to manage that aircraft in such a difficult state. Coming closer to Earth, there is a risk to power grids. So geomagnetic storms can induce high currents in power grids, railway tracks, and other long conducting infrastructure. The challenge here is that the currents induced are direct currents, whereas the power grids that we use are designed for alternating current, so they can be overwhelmed with a DC current that can cause harmonic effects and magnetic saturation of the core of transformers. And in these images on the right, you'll see a very much damaged transformer that was part of the Salem nuclear power station that was damaged during the 1989 geomagnetic storm. And this image on the top right is charred and burnt windings in the transformer. The whole transformer was scrapped and needed to be replaced. Replacing these transformers is not an easy task. As you can see, they're huge, many tons. Often there are not enough spares to cover regions if there are several damaged transformers at once. So it's one of the few natural hazards that risks long extended blackouts, which is a real concern to many countries.
Can we put a pin in that and come back and talk about it a little later?
Yes, we can. There's also risk to telecommunications. So mostly the risk is to SATCOMs and HF, high frequency shortwave communications. SATCOMs, as I mentioned before, can be disrupted through ionospheric scintillation, where signals that would have otherwise passed through the ionosphere can no longer due to the changing characteristics. And HF frequency, high frequency communications that's often used in aviation. Usually HF waves will reflect from the ionosphere that can then give you beyond line of sight communication. During radio blackout events, which are illustrated in this top picture, the frequencies that would have normally reflected would no longer reflect. So you lose the ability to have beyond line of sight communication, which could be extremely difficult when you're trying to operate an already misbehaving aircraft. So on top of this, the risk is not just to any one of these industries, but rather the most concerning scenario is where multiple industries, multiple infrastructure may be damaged or disrupted at once, leading to a cascade of failures. We live in a really integrated and interdependent society now, where there's huge dependency on GNSS for navigation and space-based services for communication and energy grids for all sorts of different industries and infrastructure. So you lose power, you lose navigation, and any one of these could cause critical loss of safe operation of critical services and perhaps even loss of lives. This is a national and international risk. So just highlighting here in the UK, we have something called the National Risk Register, which is updated every 5 or so years and basically illustrates and catalogues the main risks to civil society. This impact likelihood chart shows all of the risks that they consider on comparing against each other on a likelihood and impact estimate based on the frequency of occurrence and how impactful the event would be if it were to occur. Just highlighting a few here. Space weather is number 47 there with a number 4 and number 4. Just below the pandemic, number 54 above, that we are oh so familiar with, and things like terrorist attacks and other malicious attacks as well. So space weather extremes. Of course, space weather is something that we have in the day-to-day lives of our satellites or day-to-day operations of our satellites and space-based infrastructure in the same way that we have benign weather on Earth that occupies the day-to-day activity of our ground-based infrastructure. But the most important times from a risk perspective are those events that are extreme. And these correspond to events where there's been either a huge solar flare or a huge coronal mass ejection. And it's these events that could cause widespread disruption to the infrastructure that we previously mentioned. So one major event from history that often gets talked about is the Carrington event, named after the British amateur astronomer Richard Carrington, who observed bright flashes on the sun. This was one of his drawings on the bottom here. It's a drawing of a sunspot group where I think the dark regions are the sunspots, and then these little white beams illustrate the areas where he observed bright flashes. So we think these bright flashes were the solar flares that caused the Carrington event geomagnetic storm. This was the first observation of solar flares, and we think this is the largest geomagnetic storm in recorded history, with DST. DST is a proxy for how severe the event was, with estimates from minus 850 nanoteslas to minus 1250. There's estimates as to what this event may have done were it to happen today. and estimates in the region of $2 trillion of impact through disruption to satellite services, power grids, and downstream impacts on other services. As I was preparing for this talk, something that I got into the weeds of the Carrington event and found this dialogue between telegraph operators from the time. So apparently the telegraphs, which were basically the only infrastructure on Earth at the time that were affected by this space weather event, because this was pre-power grids, pre-space age. But the telegraph operators found that they were able to speak to each other without the external power to their telegraph lines. So the current that was induced in their telegraph lines was enough to power them. So there's quite an interesting dialogue that was recorded between different operators of telegraph lines in the US. So bringing us bringing us into the modern day, there was a fairly large geomagnetic storm in May of last year. This was the largest storm of the last 20 years, reaching a level of an intensity of G5 or KP9. These are just various other proxies that are used to estimate the severity of geomagnetic storms. There were various effects on infrastructure. So the New Zealand power system operator implemented precautionary measures to mitigate the potential impacts on their grid for the first time. This is the first time that any operator has done this. And there was significant GNSS degradation reported. But it's important to note that the impacts here were perhaps less than were expected by some people in the industry, particularly comparing the intensity of this storm to other previous storms that had caused fairly significant damage and disruption to services. So this DST index, the more negative, the more severe. So we had a minimum DST of around minus 412 for this May 2024 event. This was actually more extreme than the Halloween storm of October 2003. And this storm caused quite a major blackout in Sweden. And we didn't have anything to that extent in this May 2024 storm, maybe due to the improved infrastructure resilience. It may also be due to the limitations of this proxy. This is a global proxy, but actually the impacts on specific countries are a more local phenomena that are correlated with this, but not exactly governed by this index. So the Carrington event, while it is the largest event that we have observations of, there is potential for what we might call a super Carrington event. Such an event nearly occurred in 2012, where a huge coronal mass ejection was released from the sun and missed Earth by around 9 days. It happened to pass the Stereo spacecraft, which had in situ magnetometer data and radiation data, which indicated a Carrington scale magnetic field strength and density of that coronal mass ejection. So this video shows, maybe if I'll pause it here, this is a simulation of the plasma effects during this event. So the sun is in the middle, Earth is indicated here with this label. Stereo A was the spacecraft that was hit. So this kind of arc of plasma indicates where the coronal mass ejection was headed. And if we consider other proxy data, there likely have been events much larger than the Carrington event identified from radioisotope data. So this is concentrations of radioisotopes in things like tree rings and ice cores that can give an indication of the chronology of when that event happened. So the mechanism here is that these isotopes can be generated during major radiation events, space radiation events, as that space radiation is interacting with the upper layers of the atmosphere. And then these isotopes are sedimented on the growing trees and depositing ice cores that can then give you at least a 1 year window in which these events happened. And using data science applied to these data sets, there have been events that are on the order of 10 to 1,000 times the radiation influence, which is the time integrated flux of neutrons, compared to the 1956 event, which is the largest neutron spike in the modern era. So these were likely events that were at least as large as the Carrington event, and can be used to gave estimates of the return frequencies of extreme events that are relevant to critical infrastructure like nuclear power stations and energy grids.
Matt, question
Yep.
on that. So that right-hand plot from tree rings, anyway.
Yeah.
Is that showing one event and then the kind of decay?
Yes, exactly. So the challenge with these data is that you basically only get 1 point per year. So you get like an artificial integration over the one event that may have lasted for just 1 week or a few days.
And then you get a decay curve for the half-life of C14 or whatever.
Yeah, exactly. Yeah.
First of all, is that like the only one that shows up in tree rings? And then secondly, do we have any estimate? Like the Carrington event should show up in tree rings, should it not?
So when you say the only one to show up in tree rings, do you mean the only event or the only isotope?
The only, like I would imagine that if you extend this graph far to the right, there should be a Carrington event spike also.
Yeah. So yeah, a few things to say. There have been maybe 20 to 30 spikes in these relevant radioisotopes indicating major space weather phenomena. The Carrington event does show up, but only just. So that these proxies, you really need quite a severe event in order for them to show up. There have been, so this event in 1956 shows up more than the Carrington event. And I think this comes down to the subtleties of the different phenomena within space weather. So the Carrington event was a major geomagnetic storm, but it was more of a moderate solar energetic particle event. Whereas there are certain other events that have a much more severe solar energetic particle flux, but a much lower or more moderate geomagnetic storm. They're often interlinked, but it's not a perfect correlation.
But by the way, doesn't this also mess up carbon dating?
I'm not sure. It may do. I guess they might use different isotopes that are not affected by this, but I'm not sure. These events were first observed only about 10 years ago. So it's quite recent kind of science.
Okay.
So yeah, I wonder if it has percolated into the radio, like carbon dating literature. Maybe it has. So moving on, I wanted to cover some of the available services that are available for organizations and infrastructure operators to use to help mitigate the effects of space weather. So it's things like monitoring from space and from Earth. We have space assets that are at the Lagrange 1 point on the Sun-Earth line that give continual monitoring in situ and a remote sensing of the sun. So that gives us images like this of a halo coronal mass ejection. That is a coronal mass ejection that's coming towards Earth. There are future missions like ESA's Vigil mission that will be traveling to the L5 point to give a side-on view of the Sun-Earth line, which will hopefully improve our ability to track the speed, density, size, the magnetic field effects, characteristics of incoming coronal mass ejections. It will also allow us to look further beyond around the sun to see what might be coming in the future weeks that haven't rotated yet around towards the Earth. And then there's monitoring from Earth as well. So things like neutron monitors, magnetometers. There's a network of which are all over the Earth, and these give a good, valuable readings of space weather effects and could be used as inputs into forecasting models. You'll also notice Concord here. Why have I put that in? Because that was the one and only plane on which there were space weather radiation monitors. So there's quite an interesting data set from Concord's flights, which show a couple of ground level enhancement events where neutrons from space weather can be observed. There's some initiatives more recently that are trying to get radiation monitors on more modern flights, but this is slow going with all of the regulatory hurdles that need to be passed.
Hey, I have a question.
Yeah.
Another question. Can you go back? So that animation that's playing there from whatever it is, stereo or whatever, how come it looks like the sun just puffs out in all directions at once there?
Yeah, so it's what's called a halo CME. And it looks like it's puffing out in all directions, but it's actually because it's firing directly towards the camera.
Got it.
So it's got a sort of arc that's firing towards the camera and it just looks like it's going out. So some, but importantly not all, space weather phenomena can be forecast. And there are a handful of 24/7 space weather service centres around the world. In the UK, we have MOSWOC, which is part of the Met Office, who I work with quite closely. But in the US, they've been doing it for longer than we have here. So we have the NOAA SWPC, the Space Weather Prediction Center, who also provides some really valuable forecasting. And it provides modeling results like this in the bottom left, which I took this from the NOAA SWPC website today, which illustrates as a time lapse of a forecast of what the plasma conditions in the solar system will be like over the coming few days. I'm going to skip over that slide and perhaps go into the final section where I'll cover some points about resilience of infrastructure from the point of view of severe space weather. So this section of the talk is inspired by some of the learnings from a project that I ran over the last few years. It's been perhaps the bane of my existence for the last 2 years as I've been trying to speak to different infrastructure operators and policymakers across the UK and Europe in various different infrastructure sectors, the space sector, the energy sector, transport sector, etc. And we recently published this in a report, and I'll give you the link at the end of the presentation. But I just wanted to highlight from all of those different conversations and interviews that we had with different infrastructure operators, some of the key takeaways that I took away with regards to how to keep critical infrastructure safe and operating during severe space weather. So I'll cover each of these points one by one, but just at a very high level, to keep infrastructure resilient and safe during space weather, we want to map the risk pathways, characterize the space weather hazard, prioritize vulnerabilities, focus on resilience by design, and then resilience by operation, and plan, test, and repeat. What we mean by mapping the risk pathways, this is identifying which space weather phenomena could, in theory, disrupt the critical systems of the infrastructure that's of concern. So asking questions like whether a failure in one system could cascade into another, and identifying which of the many space weather phenomena could disrupt your systems. So from this work, we identified some examples where we think this is done quite well. So in the UK, the Civil Aviation Authority is the national aviation regulator, and they use what's called a bow tie risk analysis method to assess the potential for space weather causing an unplanned deviation from normal flight parameters. And this is a screenshot of the work that they did. It's part of a huge document, which certainly couldn't fit on the screen, but illustrates how the threats and causes can initiate what they call a top event, which is the main event that they're concerned about, and then what the consequences of that might be. Secondly, we need to characterize the hazard, and by this we mean to understand the frequency and severity of the space weather events that could impact the infrastructure that you're operating. So things like, what is the relevant failure frequency that is acceptable to your industry through the regulatory environment that you operate in? And how is this done well, or where is this done? I might be a little bit biased here because I used to work for an organization in the nuclear energy industry and do this kind of work. But the nuclear energy industry has a long history of using extreme value analysis and other statistical tools to estimate the return frequencies of 10, 100, 1,000 plus year events to estimate what the severity is. They did this a long time ago for things like tsunamis and sea level rise and wave overtopping in order to build the seawalls at the right kind of height. But they're now doing this for other hazards like space weather to estimate what the relevant flux parameters are and what the relevant current parameters are that they need to be safely operating during. 3, prioritize the vulnerabilities. So this means focusing on the infrastructure that's most critical and most at risk. So where is this done? We highlighted in this report some of the work of the National Grid Electricity Transmission, which is the UK's transmission system operator. And they've gone through systematically all of their assets, all of their transformers and substations across the UK, and tracked the various different characteristics of each of those assets that are relevant to the space weather vulnerability. So it's things like latitude, age of transformer, redundancy that they have per substation, so how many transformers are doing the same kind of job. So if you lose one, you don't lose power to that region. And they're currently using this to develop substation-specific operational procedures, which transformers to switch in and out in the event of a major geomagnetic storm. Number 4, the fourth principle is resilience by design. So by this we mean engineer passive robustness into systems so that the system can be safe regardless of its operation during a major space weather event. So the satellite industry has used radiation testing of their electronic components for a long history now to ensure that they can withstand the space and radiation environment over the satellite's lifetime. Unfortunately, things are changing in the satellite industry. As you're probably well aware, there's satellite companies now using commercial off-the-shelf components to try and get price and weight down in order to stay commercially relevant. And this means that space radiation hardening, or rather the use of radiation hardened components is being reduced, and maybe the system resilience is being reduced as well. And then we also highlight the need for resilience by operations. So we try and build systems that are resilient passively, but it's still important to build and develop contingency procedures to minimize the impacts, using things like forecasting, route diversion for aircraft, using various different response levels based on the level of space weather that's expected. The ICAO, the International Civil Aviation Organization, they now use space weather services to support resilience of the international aviation industry by providing real-time space weather advisories, they call them, which give alerts and warnings of onerous space weather conditions that may affect airlines across the world. And finally, we recommend planning, testing, and repeat. So using tabletop exercises and other types of exercises to develop and plan and test resilience plans. When I was working at EDF Energy, the nuclear energy provider in the UK and France, we ran a tabletop exercise to kick off our work in space weather resilience, and this really highlighted a number of ways in which we were ill prepared for space weather, and helped me to wave the flag that, look, this is a real risk, and look, we've just been through a scenario of a major space weather event, and things didn't look perhaps as good as people may have wanted in the room. So this triggered a huge work stream that still carries on to this day to help improve the resilience of their systems to the space weather risk. So I'll just leave this summary slide up, which just indicates those final points that were takeaways from this major report that we published earlier this year. There's a QR code here, which hopefully still works, which will take you to the repository with this report in it if you're interested in learning more. But yeah, I will be happy to take questions. So thank you.
Okay, Matt. Oh, I see Luke and Mike have questions. Well, I'm still going to use a prerogative and ask the first question. In terms of the risks to the electrical grid, transformers in particular, are there not some relatively low-cost mitigations, like installing capacitors in certain key places that can fix this? And to what extent has various countries started actually doing this?
The answer is yes, the first one, absolutely. It has been really quite frustrating how little, at least the UK, have been interested in taking these potentially low-cost routes to resilience of the grid infrastructure. So you can install DC current blocking devices in transformers. This will completely eradicate the risk to that transformer. This sounds great, but it needs to be understood what the ramifications of that are on the rest of the grid. So if the current's not going to go through that transformer, it will be diverted to a different transformer. So you can end up kicking the problem to a different transformer. However, there are certain transformers that we know are more important to maintain safe operation of. So if it's a transformer that's connecting to a nuclear power station, if it's a transformer that's connecting to another critical infrastructure, then these are the more important ones that we want to protect. I've been advocating for installing these GIC blocking devices at the most critical places in the grid.
How much do they cost relative to the?
They're very cheap. They're very cheap. Let's say about $10,000 or pounds.
Great. All right, thanks. Let's go to Luke.
Thank you so much. Thank you for your talk, Matt. Really appreciate it. I have 3 questions, but I'll only ask the first one so Micah can get to his. So the Earth's magnetic field is weakening. How does that affect the risk faced by infrastructure to solar weather or space weather?
Yeah, I can't say this is something that I have a huge amount of knowledge on. I'm aware that like the magnetic pole North Pole and South Pole presumably are moving, and I presume this is like part of the same sort of weakening and changing of the Earth's magnetic field. My sort of intuition on this is that it's probably not changing or weakening at all fast enough to be like relevant on sort of our infrastructure timeframes of a year to 100 years. That would be my guess, but I'm actually not that sure on that.
Micah?
Can this sort of space weather come from larger sources farther away, like supernova, neighboring star or anything, or is this solely a problem with the sun?
The answer is yes. So there are, as well as these solar energetic particles that I talked about, there's also what we call galactic cosmic rays, which refer to the high energy particles that come from extra solar sources. So yeah, usually what we think it's from distant supernova. These galactic cosmic rays give like a background rate of high energy radiation that is monitored and fairly consistent. And it's that background rate that is often used to design for satellites. So we can think of these extra solar sources of radiation as giving this background rate, and then the solar sources are these transient spikes in this radiation on top of the background. So your risk here is a combination of the two, and what you focus on will depend on which impacts you're most concerned with. If you're concerned with the likelihood of multi-bit upset in your satellite electronics, then you'd be concerned more with the transient solar events. If you're concerned more with the total ionizing dose of the radiation, then you'd be more concerned with the background rate of galactic cosmic rays.
The galactic cosmic rays, by the way, are heavy nuclei, from what I understand, as opposed to protons or electrons that the solar effect.
Yeah, that's true. Yeah, there are some nuances about which effects could be caused by these different sources.
Okay, back to Luke.
Great. So this is all about solar weather or solar specific weather. What can you say about the comparative risk from nuclear device EMP style things? Like, how does that compare to a KP9 event?
Yeah. Again, I think I'd be reaching the edge of my knowledge of what sort of impacts that would cause. My guess is that the disruption to the ionosphere would be similarly large, if not greater, with an EMP type device, but the radiation risk will be really quite different, I would guess, with different sources of radiation. But yeah, I would have to look into that.
Okay, back to Micah.
Solar flares and coronal mass ejections are always illustrated as giant walls of fire. As a human standing on a planet with no magnetosphere or anything, would you actually see or feel them in any way, or would it just be something you wouldn't even notice? Again, as a human with no tools.
It's something you wouldn't even notice. But if the radiation is high enough, you might notice the acute effects of the radiation.
I wonder if anybody cares about Mars. If we're talking about humans on Mars, it has essentially no magnetic field, and interesting to know what its profile is.
Yeah, I think this is a major concern for long-term space travel. I am aware of some designs of active radiation shielding, generating active magnetic fields, like a sort of mini Earth's magnetic field.
Yeah,
in order to
caves and all this stuff. Okay, we have one.
Yeah.
We have a question in the chat. Sandvik, do you just want to ask it, or do I need to read it?
Am I audible?
Yeah, it can be.
Yeah, we can hear you.
Thanks, Matt. Thanks, Matt, for the wonderful presentation. Yeah, because I put down 2 questions. The first one was regarding, does your study or in the report highlight any of the present gaps in the observation side or the modeling side in terms of forecast or nowcast that would help the current stakeholders that are at risk from the space weather? And second, do you see any rising interest in the private sector, from the private sector players who are doing anything in this domain? You may be sending new satellite observation sensors, or maybe setting up ground sensors, or anything of that sort. Yeah.
Yeah, the report covers that briefly, but it's not the focus. We cover briefly the importance of things like Vigil and some other missions that could fill in some gaps, but it's not been the focus. The focus was more about like how the downstream infrastructure operators could use available space weather services to improve their resilience. Because that's what we thought was the main important hurdle to infrastructure resilience. Because I think we actually have an overhang of data that's not actually being used, and an overhang of services that are not actually being used adequately in order to improve that space weather resilience.
I'd like to thank you for the talk, and I'd like to take prerogative to ask the last 2 questions.
Of course.
What Lydia wants to ask the standard foresight question, but the technical questions are: one, what does the Solar Dynamics Observatory contribute in a substantive way to this kind of prediction? That's question 1. And then question 2 is just your comment on the following. As a person who works for a company that operates a fairly large constellation of satellites, I will say this: the largest source of uncertainty in our orbit predictions for our satellites is atmospheric drag, and the largest source of uncertainty in atmospheric drag is solar weather.
Yeah, great. Sorry, I forgot the first question. Could you repeat that?
How does that?
Oh yeah, of course. Yep. Yeah, SDO is primarily a science mission rather than an operational mission. So the data is used a lot for improving our understanding of space weather. So often using kind of data that's not available in real time, but looking back at previous events and how the effects were related to the phenomena that were observed on the sun. There are other missions like the ACE mission, the Discover mission, this upcoming Vigil mission, various satellites that are in low Earth orbit doing in situ magnetometry and auroral observation and things that are primarily used for operations. So the main distinction here being the timely availability of the data. If you're doing operational space weather services, you need the data right now in order to drive your forecasts as far ahead as possible.
Thank you, everyone, for joining. Thank you, Matt, for the great presentation. And we'll see you next month.